Now let's talk about continuity equation. Okay, so let's start from electrodynamics. We know in electrodynamics that the total charge is always conserved. Okay, but the important thing about this conservation is that this conservation law is local. Okay, is not non-local. For example, non-local conservation it could be can lead us to a very strange situation. Suppose I have a system here. If this conservation is non-local, then it means the charge here can suddenly disappear. But this charge has to be conserved. Okay, so there's sink here, which just observed, and it just charge will the same charge, exactly the same amount of charge will pop up here. Okay, here it appears. So this system is also gives you charge conservation because Q here has disappeared, and the same amount of Q has appeared here. Okay, but what we know from the charge conservation in electrodynamics is not of this type. Okay, it is locally conserved. It means that if charge has to, for example, if charge, suppose you consider a very small region here, if charge flows in, okay, then the density here has to increase. If you consider a very small region here, where there was many particles, if the particles leave this place, then the charge density should decrease here. Okay. So usually this local, so charge is not just like disappears and appears. Okay, this is not true. It has to be locally conserved. Okay, if charge disappears from here, it should also appear here at the same point, not anywhere else. Okay, so usually this local conservation law is written as a continuity equation. So if you consider a region, a very small region, or very large region for that matter, it doesn't matter. If charge flows in, the density has to increase. Okay? Because that is just what the charge conservation says. If charge just flows in into some surface here, the density has to increase. But we know that we can calculate actually the flux. Okay, the charge passing through this area per unit time, and that is called flux. And divergence of the flux measures how much charge is flowing into this region. Okay, and if this one is true, then it has to be, because flux is coming in, we know that this has to be negative. It has to be negative. Okay, remember that if you have a vector field, and if you consider a small region here, and you calculate the flux, and if the flux let's call this vector field J, electric current. Okay, if divergence J is positive, it means more electrons. The amount of electrons that coming in is less than the going out. Okay, so that is what is we know is meaning of divergence J. Okay, So if divergence J is positive, then the flux or the electrons coming out is always positive. But what it means is that since more electrons are coming out, the density here should decrease, because charges are just, more charges are coming out. So the continuity equation basically has to be plus is equal to 0, because if this one is positive, this one has to be negative. Okay? If more flux are coming into this surface, through this surface, then divergence J is negative. But since more charges are coming in, the density should increase. In this case also, round T over round plus divergence J, it has to be 0. So what I'm trying to tell you is that this sign has to be plus. This one is negative, this one is positive. This one is positive, this one is negative. Okay? So that is the continuity equation. And this continuity equation tells you that charge is not only always conserved, but it is locally always conserved. Okay? So this continuity equation is minus here. Okay? That is what we know, what is divergence is defined, how define divergence. And this one simply says that if again, just if the charges are more coming in through this space, and the variation of that total charge flowing in into the this surface, okay, or into this volume, is just equal to flux. Flux is minus of flux is just how many charges are flowing in per unit volume. So I forgot, divergence J is what? Net flux divided by volume. If you remember this, I forgot about this. I did mention this one, but to understand this exactly, you need this one. Okay? So if you just integrate this over just, so divergence J times delta V is equal to net flux. Okay, and that net flux, how is how many how is charge density changes, and that is this one, and right hand side is this one. Okay, and that is equal to this one, according to what? This from here to here, you know, is Gaussian. So I'm not going to prove this, but anyhow, so the continuity equation is round over round T plus divergence J tells you that charge is always locally conserved. And from this, of course, you can derive this Q, the Grover conservation, by integrating, and this one is Q. Okay, so it says dt over dq is equal to, since this is surface, if you take this surface very large, where the charge density is 0, so charge density is 0, so it is 0. Okay, so Q is constant. So this charge conservation can be derived from this local conservation. Now, the reason that we mentioned charge conservation is that there is also similar conservation in quantum mechanics, and that conservation of this quantity. Okay. Also have globally conserved quantities, which is analog of Q. Okay. And this one also is local conservation. It means that there is always a continuity equation that we are going to derive. Okay, so let's see how this argument goes in this case here. So this one is always conserved. Okay, this is exactly like the charge density here, for example rho, which is Q. So psi 0, we know physically has to be normalized to 1, and this one has to be conserved. So that has to satisfy some form of continuity equation. So if I let's say psi is some gamma or p, then it should also satisfy p plus divergence of flux should be 0. Okay, so let's derive this thing, and if you integrate this over a large surface where psi vanishes, then you get that equation that this one, the integral of this, which is total charge, is always constant. So the derivation is not so easy, not so hard. So here P is defined to be probability density, which is psi xt and psi xt, which is precisely like charge density. Okay. So what then you want to have P over around T plus divergence some current associated with this is 0. What is J here? So to derive this, this book is also written in detail. So you start from here, H is equal to minus Harvard square over M square plus. So this is time dependent Schrödinger equation. And then if you take complex conjugate of that, then my Harvard carries minus, and this one minus Harvard, this one H psi t is just H is the same, and this one. Okay. Multiply this by psi, and the original this one by psi star. Okay, and subtract it, then you find that this one psi star psi, the left hand side you subtract it, you have plus here. Okay, so you have subtracted it, you have plus here. On the right hand side you have minus Harvard squared. One was psi square psi, this one cancels, psi star with psi cancels, and you have minus Harvard squared. The original one is psi star minus, and we multiply this by psi here. Okay? So this one is nothing but then just the differentiation of this one minus Harvard square diverge. So you have here some function. I think everybody is familiar with this. Is equal to divergence f gradient g minus divergence g gradient f. Okay, you can just do the computation here. If divergence a b is equal to gradient a times b plus a divergence b. Okay, so if you do the first thing, gradient f will cancel gradient g and gradient f, and if you act here, it gives f Laplacian g minus if you act here g Laplacian. So you just use this one and you can show this one, and that is precisely the current associated with this probability density. Okay, so this equation, if I define this thing to be J, it can be written as ln T over ln P plus divergence J is equal to 0, and that gives you the local conservation, and integration gives you the global conservation of this integral. And that physically means that the probability, total probability, is always conserved, and in physics it is normalized. In quantum mechanics it's normalized to be 1. Okay? Psi should be psi xt. Okay, so this one basically comes from psi t is equal to 1, and if I insert dx here, x here, then it gives you psi xt and psi xt. Okay, start. So here is using the different notation for J. Okay, so that is just continuification, which is the analog of lambda t over lambda low plus divergence electric current density should be 0. Okay, so this again leads to local conservation laws. The locally change in the probability density must be equal to negative of the energy flux. Sorry. Should be equal to the negative of energy flux. Then this negative sign is explained. If this increases, then it has to decrease because total has to be conserved. In other words, probability cannot suddenly change at these distinct points. So this one tells you very important thing about this mathematical properties of psi is a continuity equation, and that it means that psi has to be continuous. So, for example, if psi wave function looks like this, then there is a big problem, because we know that, suppose this is x point, we know that psi squared, psi star x0, psi x0 is probability that the particle is bounded, probability density at x0. But if this is continuous, then you have two probabilities at the same position. Well, either you have this one or this one. So this probability cannot abruptly change here. And that is a consequence, of course, of the continuity equation. And psi and gradient should be continuous function for regular potentials. So let's look at this again here. Let's note that for states, the Schrödinger equation is a second order differential equation. So this one cannot be discontinuous, and this one also cannot be discontinuous. And let's see how you can prove this. So let's consider this equation, which is time independent Schrödinger equation. And if I just integrate, so what is the equation? The equation was 2m half square over d square over dx square uex, okay, should equal to dx square plus this one is p, 2m over p squared, and vx uex. Since this is, we are considering it in a definite state, should be euex. So it means d square over dx square uex should equal to half bar 2m over half bar squared times, we just push this into here, Vx minus E times Ux. I'm sorry, this is minus here. So you push this into here, it gives you Vx minus E. So that equation is what is written here. So now let's integrate this from some point. So let's take x equals xi, this is xi, and consider xi minus epsilon, and here xi plus epsilon. Okay, so integrate it. Okay, then that should equal to this one. Now this one is already, this one is just dx over du prime ex. So if I integrate it, it is given, it gives you u prime xi plus epsilon minus u prime xi minus epsilon. Now this difference is given by this one. So if E is constant, then obviously as epsilon goes to 0, that is 0. For this one to be 0, it means it must have a unique derivative, then this one has to be. But this one is always true for continuous potential. Okay, if potential is continuous, then this one is always true. So that is 0. Okay, so this one xt and psi prime xt should be a continuous, at least for continuous potentials. Okay, this one has to be continuous because this gives you probability at x. This one can be shown to be continuous for a continuous potential. Okay, so that is the two boundary conditions that we are going to, for example, use when solving the actual problem. The last topics in this chapter is Schrödinger picture and Heisenberg picture. Okay, so we have seen that basically they satisfy d over dt psi t is h psi t. Okay, now here you have put s in this s, meaning Schrödinger. Okay, so in this equation, the psi, of course, the solution is given by this one, and the Hamiltonian is, of course, assuming that it's independent, is independent of time. Okay, so let's further assume that some operators does not have express time dependence. Then the expectation value of this operator change with time according to Ehrenfest theorem. Okay, so even though the operators do not have time dependence, the expectation value of the operator, which are physical observables. So this equation just simply tells you that omega and h does not have any express time dependence. Express time dependence, but the expectation value have time dependence. Okay, changes with time because the state vector bring in time dependence. Such a description where time dependence is carried entirely by the state vectors is known as Schrödinger picture. So you have written S script here. Okay, so in Schrödinger picture, H and omega, for example, assuming that this is time independent, they just stay the same. Okay, the state changes. Okay. On the other hand, we can think of description of state vectors does not have any time dependence. So what you do is, suppose you have psi st and some operator times psi st. Okay, so this is in Schrödinger picture has a time dependence, and now the omega is independent of time, and the time dependence is purely carried by the solely carried by this psi. But we know the solution, so let's write it as psi 0 times exponential I over half bar h t and omega, and then psi st is exponential minus I over half bar ht and psi 0. Okay, so if I write this one as omega Heisenberg, let's write that as a Heisenberg here. So the same expectation value can be interpreted as measured in a given state, where now omega changes according to this definite similarity transformation. Okay, this is called similarity transformation. If you have an operator or matrix H, and if you have unitary operator or any operator, this one is called similarity transformation, which is very useful, for example, in diagonalization or something. But the interpretation here is that the state remains fixed, but the operator change. Okay, so that is the Heisenberg picture here. When you do the expectation value here, that this one remains the same, and this one is just this one. Okay, here. Now we have defined Hamiltonian. In Hamiltonian picture, the operator is related with Schrödinger operator in Schrödinger picture in the following manner. HT. Okay, so let's check what kind of equation they satisfy. So I want to let's go directly here, because this result can also be derived directly. So let's look at dt over d omega h, which is equal to here. If you add it here, it will give you I over half bar exponential I over half bar ht times h. The h, since h commute, this is the same as writing h in front. Okay, if you differentiate this with respect to, assuming h is independent of time, and then you have omega s. Okay, exponential minus I over half bar ht, plus if we differentiate this one, you have I over half bar. Let's assume that the Schrödinger the operator or the original operator is time dependent, so exponential I over half bar ht times omega s over round omega s over round t exponential minus half bar I over half bar ht, plus now you differentiate the third term, which is I over half bar exponential I over half bar ht omega s. You have now here minus I over half bar, and then h time differentiate this, so h exponential minus I over half bar ht. Okay, so let's write these things first here. Okay, so you can define this operator is the time derivative operator of omega in the Heisenberg picture. Okay, sorry, you don't need this one because you just differentiate the second term here. Okay, so this one you define to be the time derivative, partial time derivative in the Heisenberg picture. So let's write it around omega h. So this one I defined omega h. Okay, as it is written here. That is the time derivative of original Schrödinger operator in the Heisenberg picture. And the remaining two terms, you see here, has a common vector. Let's write these things first here. Let's see this written here. So minus I over half r. Okay, then this one has exponential half bar over I over half bar ht times omega sh exponential minus I over half bar ht. Okay, and minus, this is minus minus plus, this minus exponential I over half bar ht. Here h is first, so h omega s exponential minus I over half bar ht. Okay, so that is written as round omega h over round t minus I over half r, and this one is the commutator of omega h minus h omega. So let's you see here, this one is this here. Okay, since h and h commute, I'm going to put these things into back. Okay, then it gives you exponential I over h ht omega s times q minus h. So that gives you omega s h. Here they commute, so I'm going to write this, push this in front because this h and h commute. Okay, then it gives you wait a minute. It gives you minus h times this one and this one and this one, which is omega s. Okay, so that is equal to omega s, omega h times h. Okay, so exponential omega s times this one is operator in the Hamiltonian picture. H and the exponential omega s is omega h, and h I put it in front, this one. So that gives you this equation. Okay, so this is very similar equation. If you remember, in classical physics, it is dt over d omega. Some function in phase space is, if omega depends on time, round omega over round t plus omega h. Okay, So the operator in the Heisenberg picture, the time evolution is precisely given by the classical consideration. Okay. So this describes the time evolution or operators in the Heisenberg picture, which is quite analogous to the Hamiltonian description of classical mechanics. Okay, we can also derive. Okay, so I just derived this by direct substitution. So this equation I just derived. So let's just summarize what for this picture. In the Schrödinger picture, psi s changes according to this rule, whereas the operator omega s is just remains the same, where in the Heisenberg picture, the psi h is just psi 0, whereas the operator now changes according to Schrödinger times exponential minus I over half bar ht times exponential I over half bar ht. Okay, so they give you the same expectation value, omega s psi st is equal to psi h, which remains constant, whereas the operator changes according to this psi h. Okay, and this satisfies the very analogous classical equation of motion of round omega d omega h over dt is round omega h over round t plus 1 over I h bar times omega h times h. Okay, so that is what we just derived from here, omega h. So these two pictures just you're observing the same omega in different frames. Okay. Now in chapter 4, we are going to discuss some application of Schrödinger equation to simple systems. Okay. So in these lectures, we'll apply the principle of quantum mechanics described in the last chapter to study some simple and one-dimensional quantum mechanical system. And of course, this will bring out the essential feature of quantum mechanical systems, and will also illustrate the differences of such system from their corresponding classical system. So what is the simple system that we are going to consider? Of course, the simplest one is just free particle, have no potential, move freely, and we're going to study this system. You'll see that the free particle, the quantum mechanical free particle, indeed behaves very differently from the classical one. Okay, so we'll see what is really how is quantum mechanical description is different from classical physics. So let's consider a free particle, and it satisfies Schrödinger equations, and h is just minus h is equal to 2m over p squared, which is equal to p squared over 2m, which is equal to half bar k squared over 2m. Okay, and it acts in functional space as differentiation, so this equation just becomes this one with no potential, and it can also be written as this one. Okay, so in this form it resembles this equation. For example, you have a h or a gamma xt, which is, for example, given by k round x squared or round square gamma. Okay, some of you may realize what is this equation. There's no I here. Okay, so this is heat equation. So basically it's different from this factor I here. Okay, so if we know some of the solution, then it can be used here. Now, you see, this is like the heat equation, except that the coefficient has an imaginary number, okay? And the solution to this equation is written as this one. So, it's just written here as a solution of this equation, heat equation, like lambda T over lambda psi xt was equal to I half over 1 2m over p squared, which is equal to round x squared over round square psi xt. Okay, so that was the equation. 2m, however, if you have on the right hand side also however here minus here, so 2m over I however, sorry, 2m over I however here, sorry, I however. Okay, the solution of this heat like equation is given by this. Okay, so let's use some of our knowledge to derive these things. Okay, so we know that so this one, actually, to solve the equation, this equation, remember this one is always given by this one. Since this function is given x space, we need to know to specify psi x0. Okay, so here you see you just adopt psi x0 from here and then use this equation that indeed the time evolution is given by this. So what is x equals 0 here? So x equals 0 is some normalization, okay, so this will not be, I will just leave all this normalization as an exercise, and then you have exponential minus x squared over 2a squared, okay, when t is equal to 0, when t is equal to 0, minus x squared over 2a squared with some normalization. Of course, the normalization can be immediately calculated using the Gaussian integral. So I leave that as an exercise. And how can I show that if the initial wave function is given by this, then the final wave function psi xt, okay, is given by this. Okay, and we know that ut governs the evolution, so you should be able to go from here to here. Okay, so this can be seen easily. First, what you have to do is you have to take the wave function at arbitrary time t, which we know is xt. Okay, and that it is x ut times psi 0, where u is equal to exponential minus I over half bar. Okay, in this case it's just p squared over m squared, which is half bar squared k squared. Okay, k is operator, p is equal to minus ik. I'm sorry, p is equal to half bar k. Okay, remember this one. So differential operator k is just k is equal to minus I differential operator from chapter 1. So to apply this in here, you see this one has to act on the eigenfunction. Okay, so the first step you do is just what? Insert here the completeness relation dk from minus infinity to plus infinity. Okay, then u given by this k operator, the k cat is the eigenstate of this, and you can immediately get this. So you have here x exponential minus I over half bar squared k squared over 2m times integral can be taken outside, so let's write it in front. Integral dk minus infinity to plus infinity, and k and psi 0. Okay, so here now is operator, but k is acting on k, so k is this number here, and it has to be integrated by minus infinity to plus infinity. We have just used k operator here. Let's just put hat here to distinguish from this number to operator. What I have used in this step is just k times k. Okay, in going from here to here. You put this into here, you insert identity here, this k hat acts on k, gives you k, so it gives you this one. Now, the initial configuration is, if the initial wave function is given k space, this can be just integrated immediately, but initial space is given by k space here. So, what you do? You have to insert here what? You have to Fourier transform basically, but that is just this, insert this identity from minus infinity to here, and that basically gives you the Fourier transform of this psi x in k space, or psi k in x space. Okay, because this is the information given. So put these things in here, you have minus infinity to plus infinity dk x exponential minus half bar over I times, now even here, let's use these things first here. Even here now k is just eigenvalue. Okay, so this is number, so I can just take it out, exponential minus I over half bar. Let's also make it half bar cancel, so minus I over 2m half bar k squared. Okay, and xk, we know what is xk. This is plane wave, and here you have what? Integral over x. Let's distinguish this x from this identity, let's put x prime here. Okay, so you have integral minus infinity to plus infinity kx prime and x prime psi 0. Okay, so this is basically Fourier transform of this one. Okay, so that gives you, since this one is given this by n, where n is just constant, so it has n times minus infinity to plus infinity dk. This one, let's write it first. Let's write this first. Exponential minus I 2m over half bar k squared. And this one we know is square root of some normalization. Okay, that changes this normalization, and exponential I kx. Okay, and then this one is integral minus infinity to plus infinity dx prime. This one also has some normalization, so I have another double prime and exponential. Now this one x is first, so it's the conjugate of this, so it is minus I k x prime times this one is exponential minus x squared over 2a squared. Okay, so we'll do this integral first. Okay, and then so let's make some space here. Okay, like this. So we have here this one. Let's evaluate these things first here. So let's put this as x. Just let's call it gamma. Okay, so gamma is basically given by gamma. Sorry, is equal to given. What's the matter? Gamma oh, there's some problem. Okay, so then maybe I have to find spaces among the here, because somehow this PowerPoint is just going crazy again. So let's do it around here. So and we'll also find some space here. Okay, so let's use all this space here. So gamma is equal to minus integral infinity plus infinity dx prime. So here you see it is exponential minus x squared over 2a times exponential minus I k x prime. Okay, so how do you do this problem? We know that this x, as x goes to infinity, this one goes to 0. Okay, much faster than this. This oscillates, but this one goes to 0. So the integral should exist. Okay, so here we are going to use the fact that if you integrate from minus infinity to plus infinity, this is basically of the form exponential minus, for example, alpha x squared, where alpha is positive, plus beta x. Okay, it doesn't matter whether this is imaginary or not, because the convergence is guaranteed by alpha positive. Okay, so I'm going to write it as minus infinity to plus infinity exponential minus alpha x, for example, minus 2 alpha over beta squared. Okay, then the first term becomes minus alpha x squared. The second term becomes minus 2 cancels, so it's x beta x. Okay, since I have then the third term becomes minus 4 alpha beta squared. So if I just add exponential beta squared over 4 alpha, okay, then it's just identity. But this one is independent of x. So this integral is just again square root pi over alpha, because I can just translate this to new x prime, and since the integration is minus infinity to plus infinity, it doesn't change. Okay, so this is square root pi over alpha. So here times, of course, exponential beta squared over 4 alpha. Okay, so if I do the integral here, I can just use this. I told you this one doesn't matter whether beta is real or imaginary, because the convergence is guaranteed. So if I apply here, so beta is just what? Beta is just minus I k, and alpha is minus. So alpha is 1 over 2 alpha squared. Okay, so that integration will give you another constant. So I am just leaving this as an exercise for you to verify. So it should equal to n now some constant times minus infinity to plus infinity dk exponential minus I, let's write it, haba k squared over 2m, and here minus, I put minus out here, so I have minus ikx times this integral, which is beta squared over 4 alpha, just gives you what? Exponential beta has I factor here, so it must have a minus sign, so it has minus k squared a squared over 2. Okay, so that is what is coming from here. So here again, now there's only integral over k now remains. So again, I can use this integral again, and then the job is done. Okay, so let's just write these things again in the Gaussian integral. So okay, so maybe this much is enough. So this equation now is some constant times, if you look at this here, now again I can this k squared is positive, so it really doesn't matter whether k squared coefficient has the imaginary or not, because this a squared is positive always, so the convergence will be always guaranteed by this factor when you integrate over k. Okay, this is k. So this I can write it as minus infinity to plus infinity dk. Let's correct terms with a squared. Okay, so exponential minus it is a squared over 2 here, plus, from here I have the minus is minus here, so it is plus I h bar k squared. I'm going to put it out, so it has I'm sorry, you must have t here. Okay, how about e times t, sorry, t, e energy times t is the evolution operator. So how about t over 2m times k squared okay, and minus ikx. Okay, so I have to do just this integral here. Now again, I'm going to use, it really doesn't matter now. This is physicist way of doing it. I can apply this even to alpha imaginary as long as real of alpha is positive, as is in this case. Real of imaginary. So here alpha is this one, but real of imaginary is always positive because it's a squared. Okay. So this one also gives you, if I do this, write this in this form, it will always, you just identify here, it's given by beta square over 4 alpha times some another integration constant. Okay, so that should give you another integration constant times this one. Now 4, you just have to calculate 4 over alpha times, but in this case, you see, this alpha is not a integration constant. Is not a constant. Okay, so it is not a constant. So the alpha, square root alpha here gives you square root a square over 2 plus I h bar t over 2m. That is this part here, this alpha, square root alpha, and pi, I have to put it into another place here. That is 1. So that is coming from this square root pi over alpha. Alpha now is function of t because it has, so this one times exponential, you have beta square over 4 alpha. So beta square is this one, k square. I'm sorry, x square, because we are integrating about k. It gives x square times divided by 4 alpha here. Okay, so that gives you exponential 4 times alpha a square over 2 plus I h bar t over 2m, okay, over x squared minus, because it has I here. Okay, so 4 is 2 times 2, so I use 1, I just leave 1 2 here, and the other 2 just cancels here. Okay, now I can also factor out square root 2 to make it another constant, and look, the final form here, that is a squared plus I h bar t over m. I have just taken out square root 2 on both here, times exponential minus x squared over 2 and a squared plus I h bar t over m. So this is precisely, up to a normalization constant, this is precisely this wave function. Okay, so you see, we see the usefulness of this evolution operator. Okay, so whenever Hamiltonian is given, you can just adjust it and go through this this one, psi t is equal to exponential minus I over half ht over psi 0. Okay, we start from here, and you immediately get this wave function. Okay, so that is the technical details. So let's discuss the physics behind this. Sorry. Okay, so if you square it, okay, we have just computed, it's easy, just take complex conjugate of this and you get this one. If you just take the complex conjugate of this, okay, psi was like some normalization, let's call this n, and it's like a squared plus m over I half a t square root over exponential minus x squared over 2 1 over a squared plus I half a t over m, I think. Okay, so you just take complex conjugate here, a squared I half a t over m, 2a squared I over half a t. And everybody knows how to take complex conjugate of this, and you calculate it to be this one. Okay, now this one is, we know this is probability distribution. Okay, or probability density is described also is Gaussian, because it is a function of the verb exponential minus x squared over some width now, but width which was originally 2 alpha, some constant a, was now given by this one. The width is given by this one now. Okay, so initially that was a Gaussian way. If you observe these things, as t evolves, the width, okay, becomes larger. So if you just look at this, if you just observe this for a long time, it just begins to like this. And as time goes, as t goes large, then the height, okay, so that's just, it looks as if the particle is just diminishing for over a period of time. Okay, so it cannot just stay in this form. It has to the wave, the amplitude has to diminish, has to become lower and lower, and that is called dispersion in quantum mechanics. Now, even if the original was Gaussian and the width was a, so if a goes very large, then you can prepare a very localized initial state, but even this one has to disperse as time goes, because the width which is given by this alpha, now the width grows. Okay, so we say that by choosing an appropriate a, you can localize the particle very well initially. You can localize it very well initially, but as time grows, the width of the Gaussian increases. Okay, so this is known as the dispersion of the wave packet, and this is a general feature of most quantum mechanical systems. Okay, now some of you may wonder, what about the initial state that is not just at rest but moving with some momentum? Okay, and then the initial state is not just exponential minus x squared over 2a squared, as was given here. Okay, but the x now, so this one is the initial state is just here like this. Suppose the initial state is given in such a way that this one is moving with some momentum. Okay, Then you can, of course, some normalization. Then this wave, this initial state can be described by n, another n, the same n, exponential minus 2a squared over 1, and x minus p0 t over m squared. Okay, and times exponential half over I p0 x. So this wave describes the initial state. I'm sorry, the initial state moving is not this one. This one is the same as x squared, but just just give the plane wave here. So this means that this wave packet is moving overall with the initial momentum p, so initial velocity with initial velocity m0 over m. Okay, so that is the case. So I want to erase this because that is, let's write it more formally here. 1x squared, but initially it is moving, so exponential I p not x over half. Okay, so this wave packet is that initial Gaussian, this one is Gaussian, is moving with the momentum p0. Okay, so here is p0 is positive, then it's moving this way. Then of course you can do the same go through the same steps, and I will just give you an exercise for you to verify, so that the Gaussian integral becomes more complicated because you have extra this factor here, but the steps are exactly the same, and you get psi xt is equal to some normalization and times this factor is the same, 1 over square root alpha a squared plus m over I h bar t. Okay, so that is what was written here. A squared plus m over I h bar t over m. And then it's very complicated. Okay, so this is just even adding just this simple term, but the I mean the interpretation is very simple. So you have this one times exponential minus x now minus, because this is moving, you have p squared t over m. Initial speed was 0, but as time goes, this is moving, and but the width is still dispersing 1 plus I h bar t over a squared. Okay, times this plane wave vector exponential I p0 over half bar times x minus p0 t over 2n. Okay, so you see the situation here is since this is moving now p0, the Gaussian shape is preserved, but Again, it disperses like this. Width becomes wider and wider, but still moving at P0. Okay, this one shows that the center line, the Gaussian center line, is moving with P0 times T. Okay, so that is the first example and most simple one. H is equal to P squared over 2M. And this example will, I hope, has illustrated how to use this unit evolution operator actually to calculate this psi xt. Okay. So we'll discuss this simple problem with infinite square well and some finite well as well. So let's discuss in the next lecture.